There are no secrets to success. It is a sum of preparation, hard work, and learning. So, hello, my shimmering stars. I, Shaurya, welcome you to our victory batch. Today, we are going to start our chapter Chemical Equilibrium. Hope so you have seen the previous lecture of physical chemistry and it is clear to you. Now we are going to start very interesting chapter which is chemical equilibrium. So first of all students, we need to understand what do you mean by equilibrium. See, to define equilibrium, I would say I can use two terms to define it. One is the concentration, another one is the rate. With the help of these two terms, I can define equilibrium into two definitions. If I talk about rate of a reaction, I would say that with the help of rate, I can say that equilibrium is a state in which rate of forward reaction is equals to rate of backward reaction. While if I talk in the terms of concentration, then I would say that it is that state of system in which all the measurable properties of a system like temperature, pressure, density, volume, they all become constant. So that state is referred to as equilibrium. So shall we write this, right? So in terms of concentration, if we want to define equilibrium, it would be the state of system in which all the measurable properties such as temperature, pressure, volume, density, all of these, etc. are constant or comes in a state to be constant. Then that state of system is referred to as an equilibrium state. That is referred to as equilibrium. Okay. Now students, I am going to explain you in detail how concentration is responsible for the definition of equilibrium. As I told you, there are two terms. One is the concentration, another one is the rate. So now we are going to write in terms of rate. In terms of rate. See, if I talk about in terms of rate, all I would say that when rate of forward reaction is going to be equivalent to rate of the backward reaction, that state is referred to as an equilibrium state. Okay, so I would write here rate of forward reaction is equal to rate of backward reaction. Backward reaction. So this state is equilibrium. Now students, I am going to discuss some of the graphs with you where we are going to find out where does the equilibrium state arises in terms of these two situations. Okay, first of all, I'm going to make a graph where we are going to see the concentration as well as the progress of a reaction, and in the next graph we are going to understand equilibrium with respect to the rate and the progress of the reaction, so that we can understand these terms and we can look into the terms of the graphs. Okay, with the help of graphs we are going to see how reactants get converted into product and how does the progress of reaction takes place. Okay, so first of all, I'm going to see the graphs in terms of concentration. Now I want you all to analyze the graph which I'm going to make over here and find out what is the difference in all of these three graphs, okay? If I talk about the very first graph that I'm going to make over here is this. Here concentration will come on the y-axis and on the x-axis is the progress of reaction. This is your graph number first. Okay, this is your graph number first. If I talk about the second graph over here, this is your second graph. Here again it's concentration with respect to progress of reaction. And the last one, this is your second one. Okay, and the last third one, if I see over here, this is your concentration and here is your progress. Okay, now this is your third graph. See, when I'm talking about the terms of concentration, I have already told you the definition, the state of the system where all the measurable properties such as pressure, volume, temperature, density, all of these become what? Constant, right? That means if I'm talking about concentration over here, the point at which the concentration of the reactant as well as the product becomes constant is the equilibrium state. Now, if I say over here that let us mark 3 points. If I see this graph and I ask you, let us mark 3 points. What are these 3 points? If I'm asking you, is this point, an equilibrium point? The next over here, I would say, is this point an equilibrium point? And the last one I would say, is this point an equilibrium point? So here I've given you 3 states. That means this is your A, this is your B, this is your C. I want you all to analyze this first graph, that where is concentration of the reactant or the product becomes constant. First of all, whenever you are looking to a graph, you need to find out what are these two lines. What are these two lines? Here also 2 lines are there, here also 2 lines are there. What does it represent? We need to understand this basic term over here. See, we know that reactant, get converted into product. So what happens over here? Reactant get consumed and product are being formed, right? This is the very basic thing that I can, see to any of the reaction, any reaction. What happens in a reaction? Reactants consume and the products are being formed. That means the concentration of reactant keeps on decreasing to make the product, right? That means initially there was a reactant, but after reacting it decreased and the product increased. The concentration of the reactant decreased while the concentration of the product increased. So same situation is occurring over here. Kindly see very carefully. Here we are writing the concentration. As I told you, reactant concentration decreases in order to form the product. So here we are looking at this line. It is decreasing, while if I see this line, it is increasing. What does it states us? It states us that if this line is decreasing, this is the line for the reactant, and if this line is increasing, this is the line for product. Is it clear to you? Because the concentration of reactant will be decreasing whenever a reaction is going to occur. Now, if I talk about this graph, again, this line is being increasing from the initial 0 point. It is being increasing. That means it is which state? It is the product state, which is increasing. The concentration of product increasing, right? And if I talk about this line, students, it is being decreased. It is being decreased. So the concentration of whose get decreased to form what? We are talking about a reaction which reactant are being converted into product. That means the concentration of reactant decreases in order to form product. So this is the line again for reactant. And similarly, this case here, this is for product, this is for reactant. Okay, now you have seen what you have taken on the y-axis, what you have taken on the x-axis. Other than this, the lines which we are getting in the graph are of reactant and of product. Now the question arises again. I am asking you A point, B point and C point in the very first graph. At which point is equilibrium attained? As I've again told you, it is that state of system in which concentration, or I would say the pressure, the volume, the temperature, they are going to be constant. That is the equilibrium state. So here, if I talk about the A point, let us see the A point. What is going to happen in the A point? See, you are if you are observing very carefully, see, the concentration of product keeps on increasing, and after A point also it is increasing. After A point also it is increasing. Is it constant? No. Constant is the situation where no more concentration is being increased. It is a, you know, fixed point or a still point after which there is no more increase or no more decrease. It is a constant situation. So if I see here, after A it is increasing, that means here equilibrium is not attained, because for to attain equilibrium we at least need the concentration to be constant. Okay, now if I look to the B point over here, what I am observing, B, here there is a little bit slight increase, you know, moving towards the C point. So yes, again here concentration is not constant. You know, for whenever the concentration is constant, we are going to obtain an equilibrium state. That means at the B point also we are not getting any equilibrium state. Now looking to the C point, I want you all to, you know, correct this a bit. It is like this. Okay, as I was drawing, so it went like this. Don't get confused. It is a straight line over here. It is a straight line over here. Now see very carefully. If I see the C point over here, what I am observing, observe this very carefully. After C point, what I am seeing, it is being still in a straight line. If whether I am talking of reactant or I am talking of product, in both of the situations, see, this is a still situation, this is a still situation. It is not increasing or decreasing after C point. That means the point at which there is no increase, no decrease is a constant situation. That means whenever the concentrations are going to be constant, it is an equilibrium state. Hence, I can say that yes, here equilibrium is attained. Okay. So with the help of definition, students, you can analyze the graphical section also. Is it easy? Okay. Now moving towards the second part over here. If I talk about the second part, here I am again marking some of the points. I want you all to find out where is the equilibrium state. Okay. So if I say this is your very first point, A point, this is your B point, and this is your C point. Okay. If I look towards the A point, very first point, we now know which is the, you know, reactant, which is the product. We easily know this. We can easily identify. If I talk about reactant, what I'm observing, the concentration of the reactant keeps on decreasing, right, in order to form product. So what we are observing over here, after A, there is a little bit, see, it is going like this. A little bit decrease, right? So when there is a decrease, that means it is not a constant situation. So here there is no equilibrium at A point. If I talk about B point also, if you see very slightly, see here it is about to be constant. It is about to be, but it's not constant. It is a slight decrease, slight, very slight decrease. But if I see over here, see here you can see there is a curve. There is not a straight line. That means yes. If I talk about product also, it is increasing, still increasing from B to C. That means here also concentration is not constant. See, whenever I am talking about concentration, I am referring to both reactant, product, both. Don't consider only one situation. Do not consider one situation and, you know, give your analysis over there. No, you have to see both reactant as well as product in order to find out the constant situation. Clear? Now if I see about the C point here, after C point it is constant, after C point it is constant. Okay, so now here again what we are observing, yes, the C point is the equilibrium point when the concentrations are being constant. Okay, now let us move towards the last graph. If I talk about this graph, see, this is your A, this is your B, this is your C. See here, kindly tell me, is A point responsible for an equilibrium state? No. Why? Because at A point reactant is being decreased and product is being increased, and it keeps on moving on, increase and decrease situation. So here at A point no equilibrium. If I talk about B point also, you can see there is a slight, you know, decrease of the reactant and slight increase of the product situation. So again here we can see that the concentration of the reactant and the product are not constant here. So here also at B point no equilibrium, but here at C we can see that it becomes constant after that. It becomes constant after that. It becomes a straight line, whether it is of product, whether it is of reactant, right? So again here at C point equilibrium is attained. Clear? Now what we are going to see, the same graphs we are going to see for the rate of reaction, but the situation is now going to change. Now the tables are going to turn over. How? See, here what we have seen at only point C, equilibrium is C. See here also, see here also, see. But when you are going to make graph of rate with respect to progress of reaction, all the situation is going to change. See, again let us revise the definitions. When I am talking about concentration, the concentration should be constant while seeing the equilibrium point. Now when I am talking about the rate of reaction, I want the rate of the forward reaction should be equal to the rate of backward reaction. Now let us see in terms of rate. See, first of all, let us understand what do you mean by rate of forward reaction and rate of backward reaction. See, whenever reactant are being converted into product. See, in the previous case, I have written a reaction where I have directly written like this. Rate is being converted into product. Is this an equilibrium state? No. Why there is not an equilibrium state? You know, to represent equilibrium, we represent with it a sign. What is the sign over here? The sign over here is basically like this. This is the sign for equilibrium. Now I'm going to explain how is this the sign of equilibrium and what is this sign representing. This sign is basically representing us that reactant is now being converted into product. We no more have any reactant. Reactant is consumed. There is no reactant left over here now. In this situation, when I am talking about this situation, what I am going to see that yes, reactants are being converted into product, and yes, product also has the ability to get converted back into the reactant. Now this is what is forward and the backward reaction. Forward reaction is the one in which reactants are being converted into product, and backward reaction is the one in which product is converted back into the reactant. So two reactions are occurring over here, while if we see this case, a normal reaction, where equilibrium is not attained, where there is no backward reaction, only forward reaction is occurring. So a sign in chemistry also plays a very important role. Whenever you are writing a reaction, if you are writing in the single direction, that means it is basically which reaction? It is an irreversible reaction which cannot be converted back. While if we are talking about a reversible one, it is converted into product, and yes, product can be converted back into the reactant, which is a reversible reaction. Clear? So at a reversible reaction, we can see the attainment of equilibrium stage. Now coming back to the segment where I was telling you the rate of forward reaction is going to be equivalent to the rate of backward reaction, which defines us about the equilibrium. Now what do you mean by the rate of forward and backward? Rate of forward refers to the reaction which reactant converted into product, and backward refers to the process or the speed at which the product converted into reactant. So whenever the rate are going to be equivalent, equilibrium is attained. Now let us see with the help of graph again. This is your very first graph. Here now I am taking rate on the y-axis. When I am talking about the concentration, I was considering concentration on the y-axis. Now when I am taking rate on the y-axis, I have progress of the reaction on the x-axis, right? So here I am taking progress of the reaction on the x-axis. Okay. Kindly draw these graphs with me. Okay, students, now we have 3 graphs. Let us see the very first graph. This is your very first graph, just similar to the previous one, the first one. Now comes the second graph. This is similar to the second graph that you have seen in the previous case. Now comes the third one. Okay, my question is, are these graphs similar to the previous one? No. Why no? Because in the previous case, we have taken concentration on the y-axis. Here we are taking about rate on the y-axis. Clear? Now, here also I am going to make 3 points so we can directly identify where is the, equilibrium state. So, if we are going to see directly over here, see, if I talk about the very first over here, I have to see the rate of forward when it is equal to the rate of backward. See, again, This is the line for the product, because product concentration increases while reactant concentration decreases. Reactant combine to form product, reactant get consumed to form product, so reactant concentration will decrease and product concentration will increase. So this is the line for the reactant which is decreasing, this is the line for the product that is increasing, right? If I see in this case, this is the line which is increasing, it is again product, because we know when there is an increase in the then we observe the product. When there is a decrease in the concentration, then it is the reactant. This is for product, this is for reactant. Now you will say, ma'am, concentration you are talking about. See, I am talking about the curves over here. So I am considering the curves with respect to the formation of the product and the decomposition of the reactant. Is it clear? Now, if I see the rate, okay, how would I see the rate of forward and backward? See, rate of forward refers to when reactant converted into product. That means when reactant is being consumed in order to form product. So let us see, the reactant is being consumed to form product. And what is the backward one? When product is being consumed to form reactant. When product is being consumed. So this is the backward one. So here if I see, this is my forward one. This line is representing which one? My forward reaction. My forward reaction was the one in which reactant was being converted into product, right? And this will be my backward reaction. Why? Because now the products are being consumed to form the reactant. Now this will be my for backward one. If I see at this point, they both are equal. They both meet up. Okay, so this point is the equilibrium point. Here, this point is the equilibrium point. In the previous case, this point was not the equilibrium point, because after this point, increase and decrease in concentration was seen. Now we don't have to see the concentration point over here, that reactant is being, decreased and product is being increased. No, we just have to find a point at which the rate of forward is equivalent to the rate of backward. That's it. A point at which they are equal. So if I see over here, are they meeting at any point where they are equal? No. There is no meeting of reactant and product. That means here no equilibrium state is being attained. Here is no equilibrium. But in the previous case, we have seen. But we have seen with respect to concentration. Now with respect to rate, there is no attainment of equilibrium. Now moving to the third graph, yes, this point. When they meet up. Right? When the rate of forward reaction is equivalent to the rate of backward reaction, that point is equilibrium point. But if you remember the previous case, yes, this graph was similar. This graph was similar. Only this graph was similar. Is that clear? Now you can easily define what is an equilibrium. Right? Now you have easily understood the equilibrium with respect to concentration and rate. So very good, students. Now let us move towards the chemical reactions. Okay, if I talk about the chemical reactions, why are we talking about the chemical reactions? Yes, because it is the chemical equilibrium. So we are considering chemical reactions, and we know that basically there are two kinds of chemical reactions that we study. One is the irreversible one and one is the reversible one, which we have studied from our lower classes from 10th. We have already an idea of what is an irreversible reaction, what is a reversible. Again, I have told you just while explaining the concentration term. So when I was telling you about the concentration, I was telling you during the definition of this sign that this sign basically is used for the irreversible one, when the product can, back cannot be converted into reactant. But yes, when this sign is used, this sign is used for the reversible one, when the reactant get converted into product and product back can be converted into reactant. So first of all, we are going to see the irreversible chemical reaction, the reaction which proceed to completion. That means reactants are consumed, okay, and the products fail to recombine to give back reactant. Again, this situation we are going to represent it with a single arrow. Why single arrow? See, if these are my reactant, they are converted into the product. Now here AgCl is basically a precipitate. It will settle down. It will not convert back into these reactant. That means here reactant combine and basically form a product. They attained a completion over here, and yes, the product don't have the capacity to convert back into the reactant. So this is which state? An irreversible state. The best way to differentiate a reversible and irreversible is the sign in between these. Here is a single sign, a single arrow. Clear? And moreover, students, here in the next case you can see KClO3 when heated gives KCl plus O2. This is also a kind of which irreversible reaction, because it is reactants are being converted into product, and now the product is not back converted into reactant. Now if I talk about the second kind of reaction, it is the reversible reaction. The reactions which never go to completion, which can never complete, never go to completion, and the products recombine to give back the reactant. Yes, we can provide some conditions so that reactant could stop at a certain point, but yes, it can never go to complete. We will give some conditions, increasing temperature, pressure, and all of these stuff, but yes, it will not go on completion. Now if I talk an example over here, I can take an example of PCl5. Okay, PCl5 is basically converted into PCl3 plus Cl2. Over here, what is happening? The reactant is now converted into product, and yes, there is a two arrows over here. One is for the forward, one is for the backward. The product have the capacity to convert back into the reactant. So this is an example of a reversible reaction. Now you can easily differentiate between the irreversible one and the reversible one. Now comes the very most important topic of your class today, that is law of mass action. See, from here you are going to get a lot of questions, so you need to understand it. It is very easy. It is very easy. Okay, now if I see what is law of mass action, the rate, kindly listen to this, kindly see this definition very carefully. You will get to know what you need to understand. The rate at which a substance react, now we are talking about the rate, it is directly proportional to its active mass, and the rate of chemical reaction is proportional to the multiple of active masses of the reacting substances. We have to focus on this word. Now we are going to talk about the active mass of the reactant molecule, not the product one. Okay, so whenever you are going to use the law of mass action, which states us that rate is directly proportional to the product of the active masses of the reactant molecules. Okay, I am going to tell you a state where we are going to find the active mass. First of all, to represent an active mass, we use square bracket. Like if I'm saying active mass is represented by A, so I'm going to write that active mass in the square bracket. Now what are the units for the active mass? Okay, if I talk about the units of the active mass, it comes out to be mole per liter. Okay, because here I'm talking about if here what I'm going to see, this is the concentration basically. What do you mean by mole? Mole refers to given mass upon molecular mass. What do you mean by liters? Liters basically is unit of volume. That means if I want to find a formula for the active mass, to calculate the active mass, how can I calculate active mass? To calculate active mass, I can say that it is equivalent to, first of all, write the basic formula. Then we are going to derive some of the formulas from that. The very first formula is number of moles by volume of solution in liter. This is the formula that we can define from the units. Now, if I want to expand this formula, I can say that active mass basically is equivalent to given mass upon molecular mass. Because number of moles refer to as given mass upon molecular mass. So given mass upon molecular mass, and yes, we know that still volume is present over here. So volume here in liters. So this is basically one formula when you are being given the given mass and the molecular mass. Other than this, when you have been given in the terms of volume, what you need to do? Active mass in terms of volume is going to be volume of substance. Because the number of moles can be defined in three terms. If you see the chapter Some Basic Concepts of Chemistry, we have seen we can define number of moles in three types, when with respect to given mass, molecular mass, with respect to volume, with respect to number of molecules, atoms, anions. So first formula is with respect to mass, second formula is with respect to volume. So volume of substance divided by 22.4 into. Now here number of moles is this. We still have volume of the container of the solution, or I would say in liters. Is it clear? It was simple. Okay, now very most important thing that you need to understand. If I give you one question, One question if I'm going to give you that, calculate the active masses of 10 gram of CaCO3 in 1 liter of solution where molecular mass is 100 grams. I'm repeating the question again. If I want you all to calculate active mass, to calculate active mass of CaCO3. Okay, and I'm giving you, given mass as 10 gram and molecular mass as 100 gram, let us say. This is just an example, okay? And volume, I'm giving you 1 liter. So you will say, ma'am, this is so simple. We can directly use the formula, given mass upon molecular mass and divide by the volume. No, but you are wrong. Why you are wrong? See, whenever you are finding an active mass for a solid substance, it comes out to be unity. It comes out to be 1. That means whenever you are going to apply for the solid, whether it is a reactant, when you are going to see in the questions, in the reactions, you need to find out which is gaseous form, which is solid form. So whenever you are observing in a solid form, no students, you just have to cancel out because its active mass is 1. So you can write over here that for solids, like this is solid. So directly, if they have been asking me the active mass of this, I don't have to calculate. I know it is 1. It is 1. There is no need to, equate any formula of this. It is unity, always unity. We no need to calculate it. There is no requirement of it because we consider it to be 1. Is it clear? Okay. For solid, it is unity. For solid, it is 1. Okay. Now, students, moving to the next part over here, if I'm going to tell you the use of law of mass action, let us see. Okay, if I talk about the use of law of mass action, how we have to equate in these situations, let us consider a following reaction in which A plus B, now this is the sign for equilibrium, we attain C plus T. I want you all to write the rate of reaction with respect to forward and the rate of reaction with respect to the backward direction. So if I say that for the forward reaction, you can write over here, for forward reaction, what is the reactant? A and B. For the forward, reactants are A and B. They are being converted into C and D. We know this. Now, according to the law of mass action, let us say that the rate for the forward is V1. Forward is V1 and for backward it is V2. I'm going to tell you what I'm going to explain over here. I am explaining you the rate for the forward is V1. Now, the rate of the reaction is directly proportional to the product of the active masses of the reactant molecules. Is it clear? Now, here what are the reactant molecule? A and B. That means their active masses product will be multiplied, right? Now, if I say active mass of A into active mass of B, this is going to be my very first rate law equation for the, according to the rate law mass action, right? If I say for the backward reaction, now, for the backward reaction, you will say that, ma'am, again we need to see the reactant. Now, what are the reactants in the backward case? In the backward, C plus D is being converted into A plus B. Now, the question splits. Now, the reactant and the product splits down. Because here for the backward reaction, we have the reactant as C and D, which are being converted into A and B. Right? So here, what is the reactant? Here the reactant is now C and D. They are C and D. Is it clear? Now what we are going to do, we are going to replace these directly proportional signs over here. So when I am replacing this directly proportional sign, I am introducing, for V1 I am introducing K1 as an equilibrium constant, and for V2 I am introducing K2 an equilibrium constant for the backward reaction. So for this case I would say V1 is equals to K1 into A into B. Now, these are the active masses. That's why I am representing this in the square bracket. Okay. Now, if I talk about V2, what I'm going to get? K2 into, here C and D will come. active mass of C into active mass of D. Is it clear to you, students? I hope so it is clear to you. Now, what is the equilibrium? What is equilibrium? It is a state when the rate of forward reaction is equivalent to the backward one. Now we have derived equations for both of these. Let us write these equations. Now for the forward, that means V1 is equivalent to V2. We are going to get our equilibrium state. Now what is V1? V1 is K1 into A into B. What is V2? It is K2 into C into D. Now if I take this K2 over here and these terms over here, what I'm going to get? K1 by K2 is equals to C into D upon we have A into B. Now I have told you when the rate of forward is equivalent to the rate of backward, we are going to get an equilibrium state. That means here equilibrium constant will come, which is K equilibrium. So K equilibrium is basically K1 by K2, or if I explain it in the terms of active masses, it is going to be the active mass of the C into the active mass of the D divided by active mass of the A into the active mass of B. Is it clear to you? I hope so. This formula, you know, is very, very important. You have to mark this formula as an important. So yes, my dear students, now you have already seen this formula. This is going to be the most important formula because you are going to use this again and again in your question segment. So when we are going to see the question segment, I'm going to explain you how to, you know, execute this formula. First of all, students, here, let me tell you, here we have taken the active masses, and to calculate active masses, you have the formula. So you can use that formula here. Is it clear? Now you can correlate. First, we'll find active mass, or directly they can give you active mass in the question also. Okay, so you'll put this over here and you can find out the equilibrium constant, which is K equilibrium. Now, students, moving to our next topic, it is characteristic of equilibrium constant. See, we have seen equilibrium constant as K equilibrium, but it can be further divided into two types. Now, what are these two types, students? If I talk about equilibrium constant, it can be divided into two kinds. One is, students, Kp and another one is Kc. Now, what do you mean by Kp and Kc? Here P refers to the partial pressure and C refers to concentration. That means we are going to now divide the equilibrium constant with respect to the partial pressure and with respect to what? With respect to concentration. Okay. Now, if I see over here, this is with respect to partial pressure. And this is with respect to concentration, right? This is with respect to concentration. So, ma'am, you'll ask me that, see, for K equilibrium, we have got a formula. Now, what are the formulas for Kp and Kc? How to calculate them? See, when I am taking a case for the Kc, let us consider for Kc, first of all, because it is quite similar to K equilibrium. When I am talking about Kc, students, I am taking when my stoichiometric coefficient as 1. Ma'am, what do you mean by stoichiometric coefficient? Students, if you have seen some basic concepts of chemistry, it is quite easy for you. If you haven't seen, no issue. I'm going to tell you what I'm saying over here. See, for example, if I have a reaction A plus B gives C plus D, this is my reaction over here. And for this reaction, if I say all are present with 1 mole, this is 1A, 1B, 1C, 1D. That only 1A is reacted with 1B to form 1C and 1D. That means here this number 111 refers to as the stoichiometric coefficient. When I am considering the stoichiometric coefficient as 1, that means 1 moles, then what will be the formula for Kc? Kindly listen very carefully. Kc refers to the equilibrium constant at a concentration. Okay, and Kp refers at partial pressure. So here if I am talking about Kc, students, what is the formula for the, equilibrium constant we just have calculated? We have to write the active mass of the product divided by the active mass of the reactant. Am I right? Exactly. Let us re-revise it. These are the active masses of what? Product. And these are the active masses of what? Reactant. Are you getting my point? A and B are the reactant. C and D are the product. Now you will say, ma'am, for backward, they are the reactant. Yes, but for a general reaction, what I'm talking over here, if I have to say A, B, C, D, then what generally I observe is product divided by reactant, that's it. Reactive masses, right? So here, if this is my product, this is my reactant, then at the upper position, I'm going to write these two. C active mass into D active mass divided by A active mass into B active mass. This is the general formula, right? Now here, if 1, 1, 1 is present, that means they have a power of 1, 1, 1. That means it will remain as it is. Active mass of C into active mass of D divided by active mass of A into active mass of B. You can also write it like this. Cc into CD divided by Ca into Cb. What is this? C refers to concentration. Either you can directly show in this way. It is but obvious that whenever you are representing something in the square bracket, you are referring to concentration. But sometimes you need to see the formula. When you are differentiating between Kp, Kc, kindly mention it as Cc, Cd, Ca, Cb. That means concentration of A, concentration of B, concentration of C, concentration of D. Is it clear? Okay. Now you can either write, this is all the same way to write. Now when the stoichiometry is not 1. When the stoichiometry is not 1, what is the reaction that you are getting over here? The reaction, for example, is N1A plus N2B gives M1C plus M2D. This is your reaction. Here, N1, N2, M1, M2 are numbers. In the previous case, N1, N2, M1, M2 were 1. Here, they are not 1. So, we have given them N1, N2, M1, M3, M2 terms of, stoichiometric numbers. Now, for this general reaction, what we are going to get, Kc? We are going to write C over here. So, concentration of C, active mass into concentration of D's active mass divided by concentration of A's active mass into concentration of B's active mass. Is it correct? No, it is incomplete. Why is it incomplete, ma'am? Because here the stoichiometric coefficients are different. When they are different, then we have to mention on the powers. I told you in the previous case, they all have 1 in front of them. So the power will be 1. Hence, it is almost same situation. But here, the numbers are not 1. They are different. So for C, the power is going to be the number in front of this, which is M1. For D, it is going to be M2. For A, it is going to be N1. And for B, it is going to be N2. Is it clear? Is it clear? Okay. Now, let us see the concentration. Concentration over here, we define concentration. What is concentration? Concentration is number of moles upon volume. So you can equate over here and you can find the unit, which is moles per liter. Now students, unit and expression for Kc. What are the units and expression for Kc? First of all, expression I have already told you. If I ask about the unit over here, what will be the unit? See, what will be the unit over here if I want you all to find out? You will say for a general reaction. Let us consider one reaction. We will find the unit for them, because in the paper, this general you can do. This general you can do. But for a reaction, how will we do? So let us take a case when N2 plus 3H2 gives 2NH3, we have this reaction. I want you all to write the expression for Kc. First of all, this reaction is balanced. Yes. Equal number of reactant molecules, equal number of product molecules. We are going to write the concentration for NH3, because it is on the product side, divided by the concentration of N2 and the concentration of H2. Is it equivalent? Is it complete? No, because here numbers are present. So the power will be 2 over here. It has a power of 1 because 1 is present. It has 3. So the power will be 3. This is the expression. Now what is the unit over here? See, to calculate unit, we know that this is concentration. So what is concentration? It is mole per liter. It has a square over here. So mole per liter square divided by here. For N2, it is again mole per liter. It has a power of 1. And for H2, it is a power of 3. So, mole per liter power 3. Now, if we solve this, what I'm going to get? 1 by mole per liter square. In other words, I can write mole per liter power minus 2. Is it clear? Is it clear? So in such a situation, students, you can easily calculate the unit and expression. the unit and expression. Again, I am explaining you, whenever you are getting a situation like this, 2a plus 3b gives 4c plus 5d. I want you all to write expression. So how you will write it is very simple. For Kc, you are writing concentration. That means concentration of C. Do not forget to, put square brackets. Then the concentration of D divided by the concentration of A into the concentration of B. Now the numbers will come in the form of powers. For C, the power is going to be 4. For D, the power is going to be 5. Because it is a 5 in front of you. For A, it is going to be 2. For B, it is going to be 3. Such kinds of question arises in your examination. Is it clear? Now, I am going to give you one question. Okay. I will give you one question. You can solve yourself. 3a plus 4b gives 2c. Write an expression for this reaction. Also calculate its unit. This is your homework now. Is it clear? It's a general reaction, just a practice session. Is it clear? Okay. Now students, this was all about Kc. We move towards Kp. What do you mean by Kp? Kp basically refers to the equilibrium constant at a partial pressure, right? Okay, now this basically is applicable only for gases. Do remember this. Applicable only for gases. You don't have to forget. And yes, whenever you are going to get a solid, active mass is going to be unity. Remember? Good. This is applicable for solid. You have to take unity. I am just mentioning because so that you can't forget this point. For gases. Okay, students, now for Kp, if I talk about, let us take a general case when the stoichiometric is going to be 1. For the general case, I would say 1a plus 1b gives 1c plus 1d. Now here the expression for Kp is going to be partial pressures. We are going to take partial pressures over here. In the previous case, we took concentration. Now for the partial pressures, again, we are going to take this first on the upper side, and on the denominator side we are going to take the reactant one. So for the numerator one, we have the partial pressure of C into the partial pressure of D divided by the partial pressure of A into the partial pressure of B. Now this is my formula, my dear students. This is the formula. And for this formula, we know that they have 1, 1, 1 in front of them. That means powers are also 1. Powers are also 1. Now, ma'am, what is PA, PB, PC, PD? We don't know. But for the previous case, we know the formula. We knew that concentration was equivalent to number of moles divided by volume. But here we don't know PA, PB, PC, PD. What we have to do over here? Why are you getting so tensed when you see a lot of formulas? Learn to play with formulas. Learn to, equate the questions, the concept in the formulas. And I'm assuring you, when you practice, students, you can achieve anything. If you're starting from the scratch and you're moving, you can achieve everything with the help of just practice. Practice questions, as much as questions you can do, and I assure you, any examination is nothing in front of you. You are capable of doing anything in life if you have a determination. You are capable of doing anything if you want to achieve it. Just believe and go through the way. Just believe in yourself. Okay, so here when you are looking at the formulas, you don't have to get worried. How will I do this? Just question yourself. Why can't I do this? Why can't I do this? I will do this. I will prove these questions. You are nothing in front of me, right? Okay, now if I'm going to see here how to calculate the partial pressures, there's a formula. If I want to calculate for the partial pressure of A, it is going to be moles of A divided by total number of moles into total pressure. Total pressure will be given to you in the question, so no need to worry. Moreover, to calculate moles, whenever they confuse you, they don't give you moles directly. So what you need to do, that moles formula is given mass upon molecular mass. Is it clear? Great. Now students, I want you all to write an equation when there is when there is different stoichiometric coefficient. I have given you the case when there is 1 1 1 1 stoichiometric coefficient. Now I want you all to write first, pause the video, write first and then match with me. If I'm going to take a situation where we are going to get different, value, for example, n1a plus n2b gives m1c plus m2d. Now here the Kp value is going to be partial pressure of C into partial pressure of D divided by partial pressure of A into partial pressure of B. Here now the powers will come. For C it is m1, for D it is m2, for A it is n1, for B it is n2. Is it clear? Now you know the formula for Kp, you know the formula for Kc. We are going to establish a relationship between Kp and Kc. Now we are going to establish a relation between Kp and Kc. Okay, now students, we know that for an ideal gas, we have already done this. If you have not done this, no need to worry. What is an ideal gas equation? I'm going to tell you over here. Ideal gas equation is PV is equals to nRT. This is an ideal gas equation. This is pressure, this is volume, this is number of moles, this is gas constant R, this is temperature T. Now for these situations, if I take this V downward towards this, so I'm going to get PV is equals to nRT by V. Now here if I replace N by V by concentration, we know that concentration is basically what? Concentration is basically number of moles by volume. So if I replace concentration over here, what I'm going to get? Sorry. One more thing. I have taken this V below, so here V will not come, right? Okay, now see, I have taken this V downwards. Here I have got this. Now P is equals to C into RT. C basically is what? Concentration. Now this is the formula with respect to pressure and with respect to concentration. Now what we are going to do this, we are going to equate some of the equations over here. What we are going to do, for 1 mole, we are going to establish a relationship between Kp and Kc. For 1 mole as a coefficient, I have, for example, 1A plus 1B gives 1C plus 1D. What is Kp over here? You know that Kp will be partial pressure of C into partial pressure of D divided by partial pressure of A into partial pressure of B. Right? And all of these have 1 in front of them, so that will come in the power section. Now comes the next part over here. We know that P is equals to CRT. We know this thing. So we can write over here what is PA. PA will be equals to CA into RTC. Gas constant and temperature is constant, right? CA is the concentration of A. PA is the partial pressure of A. Now PB is equals to CBRT. PC is equals to CCRT. While PD is equals to CDRT. Here PA is partial pressure of A. PB is partial pressure of B. PC is partial pressure of C. And PD is partial pressure of D. Other than this, here CA is concentration of A, CB is concentration of B, CC is concentration of C, while CD is concentration of D. Right? Now we are going to equate all of these over here. When I'm going to replace, what I'm going to get? Kp is equals to, now what is PC? PC is CCRT into what is PD over here? It is CDRT. Okay, below, what is PA? It is CART. What is PB? It is CBRT. Am I right? Now all RT will get cancelled out over here. This RT is going to get cancelled. This is going to get cancelled. They are because in the divide section. So what we are getting over here, we get Kp is equals to Cc into Cd divided by Ca into CB. Now CC into CD divided by CA into CB. This is what? This is KC. This is KC formula. Yeah. So we can replace it. Now here KP is equivalent to KC. For which case? For which case? When the stoichiometry you took as 1. When this stoichiometry you took is 1. Then you are going to get Kp equivalent to Kc. When the stoichiometry is going to be 1. When you are taking 1 moles. Is it clear to you? It was easy for you to understand what I am going to explain to you. I have taken the case for Kp, Kc first of all as 1 mole. Then I have taken general cases. General. Now here also I have taken for 1 mole. Now I am going to equate for general case. I want you all to do this first. Please do this first. For me, students, if you want, success, so kindly follow the path which I'm going to tell you. Or you can either just, if you're going to do with direct formula, you are going to forget in your examination. You are going to remember till for few days, for 2 days, 3 days, 4 days. But when you understand from the depth of the chapter, from how it is being derived, I know that, I assure you that you are not going to forget in your examination. Now you know that when you are going to take 1 mole, Kp will be equivalent to Kc. The equilibrium constant at the partial pressure will be equivalent to the equilibrium constant at the concentration. Isn't it interesting, right? So if I'm going to take for different moles now, that is N1A plus N2B gives M1C plus M2D. Now for this situation, what is going to happen over here? First of all, we are going to write the expression for Kp. It is going to be partial pressure of C. But now power will be the number in front of it, that is M1, into partial pressure of D, power is going to be M2, divided to be partial pressure of A, the power is going to be N1, into partial pressure of B, the power is going to be N2. This is the expression. This is the expression. Now we know that PC is equals to concentration of C into RT, right? Because we know that pressure is equals to CRT. We have just calculated from the ideal gas equation. So we are just replacing, right? If I'm going to write PA, it is going to be concentration of A into R into T. If I'm going to write PB, it is concentration of B into R into T. If I'm going to write for PD, it is concentration of D into R into T. Right? Now, what I'm going to do, I'm just going to replace all of these situations over here. If I'm going to replace all over them, what I'm going to get? Kp is equals to, now PC is basically concentration of CRT and it has a power of M1. In the previous case, the power was 1, but here it is M1. Now, what is PD? The concentration of D into R into T. T. The power is going to be M2. Now divided by, what is PA? It is the concentration of A, R into T and the power is N1. Now what is PB? It is the concentration of B into R into T and the power is N2. Right? Right. Now let us separate RT and the concentrations individually. If I open up this, what I'm going to get? I'm going to get Kp is equal to concentration of C, power is again M1 into RT, power is again M1. It is the same thing because they are multiplied. I can write in this way, right? Okay. Similarly, I can open up for D, CD power M2, RT power M2. Divided by concentration of A power N1, RT power N1, concentration of B power N2, RT power N2. Now let us separate RT one side and CA, CB, CD, C one side. What is Kp? It is equivalent to C. I am going to write CC first over here, which is M1, and CD separately, which is M2. Divided by CaN1 and CbN2, and it is also multiplied with what? I am going to write all the RTs together, RTM1 into RTM2 divided by RTN1 into RTN2. Now see students, we know that this whole is what? This whole is Kc This whole is Kc, the formula for Kc. So we are going to replace over here what we are getting. Kp is equals to Kc into RT. Now something in multiply gets add on. The powers get add on when the base is same. So it is going to be M1 plus M2. This is the basic maths. When something is in multiply, the powers get add on. When something is in divide, the powers get subtracted. So here at below we are going to get RT. Now they are in multiply, N1, N2. So it will be N1 plus N2. Now as I told you, when someone is in multiply, it gets add on. But when someone is in divide, it gets subtracted. So it is in divide, it will move in the upward direction. What expression I've got? I've got Kp is equals to Kc into RT power M1 plus M2 divided by RT power N1 plus N2. Now these are in divide, so it will go and it will subtract. So what I'm going to get? Kp is equals to Kc into RT. Now here the power initially was M1 plus M2. What is going to be subtracted? N1 plus N2 will be subtracted. Now what do you mean by this, students? What do you mean by this situation? This is basically delta Ng. What do you mean by delta Ng? Delta Ng refers to number of moles of product minus number of moles of reactant. And G here stands for gaseous. G here stands for gaseous. So these are the moles for the product minus the moles for the reactant. Moles, which are the numbers which are present over here. Now students, if you study some basic concepts of chemistry, the numbers which are present over here are not always the moles. The number present in front of the A, B, C, D are not always the moles. But in this case, when we are talking about chemical equilibrium, we considered it as moles only. So do not forget. Okay. Now here, if I replace this with delta Ng, what it is going to be? Kp is equals to Kc into RT to the power delta Ng. This is the relationship that you have established between Kp and Kc. It is very, 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 very important. You are going to get a lot of questions from this formula, students. So yes, students, now this formula is going to be very, very important and you have to equate in the questions. And while doing the questions, we are going to see how to calculate delta Ng. Now let us take one example and let's move forward towards the next segment. If I talk about a general reaction, for example, 2A plus 3B gives 4C. Now what is delta Ng over here? First of all, for solids you don't have to take anything, but for gaseous, delta Ng is going to be number of moles of product minus of reactant. For product it is only 4, minus for reactant it is 3 plus 2. They both are going to add 2 plus 3, that is 5. So 4 minus 5, it comes out to be minus 1. So you have to do delta Ng in such a way that the numbers present in front of them, you have to equate that. Clear? Okay, students, now moving towards our next segment, that is reaction quotient and equilibrium constant. See, we have already seen equilibrium constant. Now arises reaction quotient. Kindly put a arrow over here. Sorry for this. Arrow will come over here. Now for a general reaction, AA plus BB gives CC plus DD. Here, students, small a, small b, small c, small d. These all are referred to as, the stoichiometry, the numbers which we use, right? So at any stage of the reaction, what we do? We say that at equilibrium, rate of forward is equivalent to the rate of backward, and we calculate equilibrium constant. But for a particular stage, which is not equilibrium, they ask you to calculate, the value of reaction quotient. What is that? See, at any stage of reaction, other than the state of chemical equilibrium, other than the state, see, at chemical equilibrium, we are going to calculate the equilibrium constant, but not at chemical equilibrium. What we are going to calculate? Let us see this. At any stage of the reaction other than the state of chemical equilibrium, concentration ratio given in the equation 1, which is the product concentration divided by the reactant concentration, the active masses, is called concentration quotient or reaction quotient. See, equilibrium constant is used when equilibrium is attained. But other than equilibrium, one term is more, which is known as reaction quotient or concentration quotient, which is the same thing, but there are certain situations over here. See, it is usually represented by QC or Q. This is the formula. You will see that this is the same formula, but where the difference arises, in K equilibrium we calculated at the equilibrium point. Here we are not calculating at the equilibrium point, we are calculating other than that point. And let us see what are the situations over here. If Q is equals to K, now K here refers to as equilibrium constant. Here K is equilibrium constant. So if Q reaction quotient is equivalent to K, then what is going to be happen? The reaction is at equilibrium because it is the same formula. When Q is equals to K, that means this is the same formula. The equation, the reaction is at equilibrium. But when Q is more than K, see, you have three situations. When Q is equal to K, that is equilibrium state. When Q is more than K, then Q will tend to decrease so as to become equivalent to K. As a result, the reaction will proceed in the backward direction. What will happen? Backward direction. In the reaction will proceed in backward direction when the Q is more than K. But when the Q is less than K, reaction will proceed in forward direction. It is very easy. It is quite, you need to compare between the equilibrium constant and the reaction quotient. This is your, I would say, this one was our rate of forward and this was our rate of backward reaction, right? So it is quite simple. When Q is more than K, it is going to be the backward one. When Q is less than K, it is going to be the forward direction. Now students, moving to the next topic is degree of dissociation. In the previous case only you need to remember the three cases, that's it, nothing else. Okay, you just have to calculate the value of Q, compare it with the K value. Okay, you will be given in the question the K value and you know when it is more, when it is less, you can directly write backward and the forward. Now comes degree of dissociation. Degree of dissociation, students, is represented by alpha. It is represented by alpha. Now for a given reaction, let us say a reaction is there. A gives B plus C. We have to calculate degree of dissociation for this reaction where reactant is A and the products being formed are B and C. Now for this reaction, students, first of all we need to understand, I always take an example of burger because I feel that yes, we can correlate somewhat here because I want you to understand what is happening with reactant and product. See, what happens, I am taking a case of burger. For example, I have to make a burger, right? And to make a burger, I require bread. Other than this, I require some salad or I would say cheese slice, right? So to make a burger, if I am considering that the ingredients in the burger, are the burger bread and the other ingredients other than the bread, right? So first of all, I only have the ingredients with me which are acting as a reactant molecule, and when I'll combine them, when I'm when I'm going to make it, then what I'm going to get? A burger as a product. So the reactant over here is my bread as well as the ingredients which I'm going to use over here. So here my reactant is A, which is burger, right? Which was sorry. Here my reactant is A, which is my requirements, which are the ingredients or the breads, right? So these are my ingredients which are present. For example, they are present in A amount. Now, initially, I want to prepare burger, but I only have the material with me. Burger is not made at that spot. That means at time t is equals to 0. That means initially, when the reaction has not been started, when the preparation for the burger has not been started, at that spot of time, we just only have the ingredients with us, right? So that means that time, when the reaction has not been started, we only have a reactant with us. Is product made? No. Until and unless we won't do the preparation, product will not form. So I would say that when time was 0, that means initially we just had our ingredients, we just had our reactant, we don't have products. That means product is going to be 0. Okay. Now what happens? At something time t, I would say, what happens? There are some moles dissociated from A. For example, let us understand this, what I am going to tell you. See, I am going to prepare burger, and how I'm going to prepare burger, I would say that if I assemble all of the things, okay, if I take one bun and I put the ingredients on it, and yes, the burger is being made after the heating, right? So what is happening over here when I cook it? I am obtaining a product with me. Now the product is going to be X. Now, what is the reactant over here? Now see, the reactant initially was something and it is consumed to make something. Okay, what happened? I had 2-3 buns with me. I had 2-3 breads with me. I want to make one burger, so I will use one bread and the ingredients and I will make the burger, right? So what I'm going to do is, from the reactants, I am taking some of the ingredients. I'm taking a bread. I'm taking some of the ingredients and preparing burger. That means some of the moles are dissociated. Now forget the concept of burger, come back to the chemistry part. Here I am saying initially we had something, now something is being lost. The thing that is being lost from the reactant, that is preparing a product. See, this was total amount. From 10 amount, I am taking some amount to prepare something. For example, I am taking out 5. What I am going to prepare? I am going to prepare 5. That means if I am taking X moles from here, then X moles are going to be prepared. Okay, this is what degree of dissociation is. Now here X is basically what? X is basically our degree of dissociation. Now to calculate alpha. Okay, these are, the moles dissociated. Not degree of dissociation, sorry, moles dissociated. Now we need to find the value of alpha, the degree of dissociation, which depends upon the formula that total moles dissociated by initial moles of the reactant. Total moles dissociated by initial moles of the reactant. So if I have to calculate over here, what will be my alpha? Total moles is going to be the moles at the time t. So I'm going to add all of them. Now at time t, reactant is A minus X plus B is X and C is also X divided by initial moles of the reactant. What were initial moles? A was the initial moles. So what is going to be the value of alpha? C minus X and plus X get cancelled out over here. I'm going to get alpha as A plus X by A. This I am to get for this reaction. But now when the reaction gets changed, if I take an example of N2O5, if I say N2O5 gets split into NO plus NO2, then I am giving you a case. Okay, this is the case, students. I want you all to calculate here. If I give you the total pressure as P and the degree of dissociation as 50%. Okay. Sorry, it is N2O3. Kindly correct it. It is N2O3. Welcome. Yes. Okay. Now, if I say the degree of dissociation over here is 50%. Degree of dissociation here is 50%. Now, when degree of dissociation is given to you 50% and the total pressure is P, calculate the value of Kp. See, what was the formula of Kp? First of all, Kp is equivalent to the partial pressure of the product, which is NO, plus partial pressure of NO2 raised to the power of the number present in front. When nothing is given, it is 1. So the powers are 1. Sorry. Here multiply will come because it is the product of active masses divided by the reactant 1. Here reactance is N2O3. So the partial pressure of N2O3 will be taken. Now students, what are the formulas for the partial pressures? If we remember, what are the formulas for the partial pressure? Partial pressure formula was moles into total pressure, if you remember. Moles of P divided by total number of moles into the total pressure, if you remember, right? Now what we have to do is, first of all, we need to calculate the value of alpha. See, N2O3 gives NO plus NO2. Initially, what happened at time t? What happened? N2O5, let us say it is 1. It was total, 1 was present, they were 0, 0. Now at time t is equals to t, what is happening over here? We say that degree of dissociation is 50%. That means we need to calculate alpha. First of all, when percentage is given, kindly see. Percentage dissociation is equivalent to alpha into 100. It is equals to alpha into 100. So here we have percentage dissociation as 50%, which is equal to alpha into 100. That means 100 will be divided, because percentage is 50%. So 50 by 100. It is going to be alpha. It comes out to be 0.5. It is 50, not 80. Okay. So it is 0.5. 0.5 is my alpha. And I know that what happens over here, a minus x, x, when here 1, 1, 1 is taken. So here x comes out to be what? 0.5, and a is the initial one. So it will be 1 minus 0.5, it will be 0.5, it will be 0.5. What I'm going to get? 0.5, 1 minus 0.5 is 0.5, this is also 0.5, this is also 0.5. Now if I put here the values for this students, what I'm going to get? It is quite easy, students. You just have to equate in this formula the partial pressures, and to calculate partial pressure you have to take the number of moles of the component divided by total number of moles into the total pressure. Total pressure is given to you P. Is it clear? Was it simple? Clear? So you can directly equate all of these and you can find out your answers, students. You can find out your answers. But whenever students, here 1, 1, 1 is given. But if 1 is not given to you, how will you do this? See, if you are being given 2a gives 3b plus 4c. Now for this, students, how can you calculate C? For this situation, when time is equals to t was 0, then this was a initially, this was 0, this was 0. When time was t, then a minus x occurs here, x is formed, x is formed. Now the numbers will come in front of the x molecules. 2 will come in front of this x, 3 will come in front of this x, and 4 will come. Now here a minus 2x will come because 2 is present in front of this. So in front of x the numbers will come. Now to calculate alpha, what was alpha? What was alpha? Total number of moles divided by initial moles of the reactant. So what were total number of moles? It is a minus 2x plus 3x plus 4x divided by initial moles were a. Initial moles were a. So we'll calculate it. We will get a plus 5x by a plus 5x by a. So this is the way to do. You know, when you are getting 1, 1, then you can directly write a minus x, x, x. When you have been given numbers, they will come in front of this. They will come in front of this. You have to keep this in your mind, students, because it is very, very important. It is very, very important. And you know, with the practice, you will get the situations. I am again writing the formula for Kc and Kp. It will help you again and again. The formula for Kc was Cc into Cd, that is concentration of C into concentration of D divided by concentration of A into concentration of B. Now the powers for this was M1, M2, N1, N2. What was the formula for Kp? Partial pressure of C power M1 into partial pressure of D power M2 divided by partial pressure of A power N1 into partial pressure of B power N2. What was the relationship between Kc and Kp? If I talk about the relationship, Kp was equivalent to Kc into RT, bracket start, power is delta Ng, where delta Ng is equivalent to number of moles of product minus number of moles of reactant. Other than this, we also find one formula for alpha, that is total moles dissociated divided by initial moles taken. Also, when they have given you percentage, alpha percentage, it is equivalent to alpha into 100, degree of dissociation into 100. So these are the formulas which I have written for you so that you could remember easily. Now students, comes our next topic. If I talk about the next topic, it is relative density, which we which is quite useful in this also and in your some basic concepts also. So if I talk about relative density and degree of dissociation, heading is relative density and degree of dissociation. Relative density and degree of dissociation. See, if I talk about relative density, first of all, the relationship between molar mass and vapor density is that molar mass is twice of the vapor density. Okay, you need to write this also. Molar mass is twice into vapor density. Okay, other than this, if we need to calculate the value of degree of dissociation, it is equivalent to degree of dissociation which is alpha, students, which is alpha. It is equivalent to capital D minus small d divided by n minus 1 into small d. This is the formula for degree of dissociation. Here D stands for, there are two D, capital and the small one. Capital stands for theoretical vapor density and the, small d stands for observed vapor density. Theoretical vapor density, observed vapor density. Okay, n here is number of moles, alpha here is what? N is here is number of moles dissociated, alpha is degree of dissociation. This formula is going to help you in your question segments. Okay, students, now we will move forward towards our next segment, that is the Le-Chatelier principle. So now let us see the Le-Chatelier's principle, students. Le-Chatelier's principle explains us that if a system is in equilibrium, whenever we are talking about a system in equilibrium, that means whenever the rate of reaction of forward is going to be the rate of reaction of backward reaction, right? So that time subjected to a change, see what happens. Whenever the system is in equilibrium, we are going to do a particular kind of change in that. That is Le-Chatelier principle. And what do we observe from that change? See. If a system is in equilibrium subjected to a change in the concentration, either you increase or decrease the concentration or temperature or pressure, the equilibrium shifts in that direction that leads to undo the effect. See, you have done an effect. To cancel the effect out or to undo the effect, equilibrium will shift in the direction that will undo the effect, that will reduce the effect. Okay, so this is what a Le-Chatelier principle is. We will see their effects in detail. You will get to know more about the Le-Chatelier principle. First of all, if I talk about effect of temperature, see, there we are going to see effect of temperature, effect of pressure, effect of concentration, effect of inert gases. A lot of things. So very first is effect of temperature. Whenever I am talking about temperature, I am thinking that my reaction is exothermic or endothermic. So this will help me to find out the effect and to see the equilibrium will shift in which direction. So first of all, what I need to do is I need to identify whether my reaction is exothermic or my reaction is endothermic. When I will be able to identify the reaction exothermic or endothermic, I will be able to identify when is heat released and when is heat given to the system. Because whenever the heat will be released or will be given to the system, we will see the shift of equilibrium, students. We will see the shift of equilibrium. What happens actually, see, if I talk about a general reaction, I say that A plus B, gives C. When temperature is increased, this is a sign for increase, so don't get confused. When temperature is increased, heat will be released. So when heat will be released, I can write it like this because it is released as a product. It is the equilibrium sign. So I said that when temperature is increased, heat will be released. And when heat will be released, students, what will happen over here? We have told that Le-Chatelier principle tells that whenever you are increasing pressure, whenever you are decreasing pressure, when you are increasing concentration, whenever you are decreasing concentration, whenever you are increasing temperature, whenever you are decreasing temperature, you have to undo the effect. You have to undo the effect. So see, when the temperature increased, heat released. Heat released, that means reaction is moving in the forward direction. Reaction is moving in the forward direction. To stop this, what will happen over here? We want this should not increase. this should not increase. How this will get reduced now? When it will proceed to backward direction. See, again I am telling you, when temperature is given, when temperature is provided, heat is released as a product. So we said that equilibrium now shifts in this direction. But Le-Chatelier principle says that to stop this effect, that temperature is increased, heat is increased, to stop this, now this we know is in more amount due to the presence of heat, right? So to stop this process, we will directly convert it into backward into reactant. That means we will what do? The reaction will proceed in which direction? Backward direction, to undo the effect of temperature. The reaction proceeds in backward direction to undo this effect. To undo this effect, it proceeds in the backward direction. And now see what happens when temperature is reduced. That means heat is given to the system. When heat is given to the system, that means A plus B plus heat is given to form C. Heat is given to form C. Heat is given to form C. That means now this is more than this. Now to reduce this effect, what will happen? To reduce this, when we have reactant more due to the presence of heat, because temperature is less, so here heat will be given. When heat will be given, then this is more. To reduce this, it will get converted. When it will get converted, it will reduce, it will consume. So now here, to reduce this, reaction will proceed in the forward direction. In the forward direction. So it is quite easy concept. Here you just need to understand, when you are increasing temperature, what is happening? When you are decreasing temperature, what is happening? See, whatever is happening, you have to reduce the effect. To reduce the effect, it will move in another direction. See, for in this case, this was moving in this direction, but to reduce this effect, because here heat is released, to reduce this, it will move in backward direction. Here, now what was happening here? Heat was given to the system to get converted. Now this is more in number. We have to reduce it. To reduce it, this will be converted into this. So we need to undo the effect. This is what Le-Chatelier principle explains to students. Is it clear you? The both of the reactions are now clear to you. When heat is released or when heat is given, what is the effect and how does the reaction proceed? I hope so it is clear to you. Now let us see. This is the case for exothermic again. This is for the endo. When heat is produced and when heat is given, this is endo. Is it clear? Now the temperature effect is clear. Now moving to the next effect, that is the effect of concentration. If I look to the effect of concentration, the very first thing is, if concentration of reactant is increased, see what happens? Reactant makes product, right? If the concentration of reactant is increased, the reaction shift in the forward direction. Why? See, whenever something is more, it will split down. See, reactant consumed to form product. That means initially reactant were present in more amount. They were making product. Same is happening over here. Reactant was present in more amount. If this concentration is increased, it will get converted into product. When it will get converted into product, the reaction moves in which direction? Reaction shifts in forward direction, right? If the concentration of reactant is decreased, when it is decreased, reaction shifts in which direction? Backward direction. Why? Because product now is more. So product will get converted into reactant. If the concentration of product is increased, now if it is increased, reaction shifts in backward direction, because when something is more, it will split down, right? Okay. If the concentration of product is decreased, the reaction shifts in forward direction. Is it clear? Is it clear to you? If any of the species is in solid states, its addition does not alter the original equilibrium. When there is solid state, it will not alter. Now these are the situations what happen. Now Le-Chatelier principle explains the opposite. To reduce this effect, it will undo the effect. To undo the effect, it will change the direction. Is it clear? Okay students, now moving, these were the effects which I have shown. What will happen when reactant is more? So in which direction the reaction proceeds? The Le-Chatelier principle says that it will undo the effect. To undo the effect, it will see the direction. Is it clear? Okay students, now comes the effect of pressure. If I talk about the effect of pressure, we know that according to ideal gas equation, PV is equals to nRT. Now, Pressure here is directly proportional to number of moles. Okay, so whenever students, whenever pressure is increased, number of moles will increase. And whenever number of mole will increase, system will reduce the effect. System will reduce. When system will reduce, the reaction will proceed in forward direction. It will proceed in forward direction. Now when pressure is decreased, number of moles is decreased, system will now what do? It will undo this effect. To undo this effect, it wants number of moles to be increased, and to increase, the reaction will proceed in backward direction. Okay, I'm again telling for the concentration part, they were the situations given you. According to the Le-Chatelier principle, you have to undo those effects. So you know the answer for that also. Clear? Okay. Now if I come to the effect of catalyst, catalyst basically has no effect. It only helps to attain equilibrium sooner, that's it. It is basically used to complete the reaction as soon as possible, that's it. Okay. And catalyst basically we get as a, similar, just the way we used it, it is attained back in the similar way. It doesn't get consumed in the reaction. It is just, it provides a surface for the reactant to get converted into product. It is that simple. Now comes the effect of addition of inert gases. The addition of inert gases, for example, helium to a system at constant volume has no effect on the equilibrium condition. Addition of inert gases to a system at constant pressure has the same effect on the equilibrium constant as does decreasing the system pressure. So you need to keep these three things in your mind, where delta Ng is more than 0. When it is more than 0, then equilibrium will shift towards the right direction. That means towards the forward direction. When delta Ng is less than 0, it will shift towards the left direction. Okay, and when delta Ng is equals to 0, students, then there will be no effect on the equilibrium. Clear? Great. Now students, this ends our Le-Chatelier principle. Now comes the characteristics for the equilibrium. We have studied equilibrium. Let us see the characteristics. The very first characteristic is at the state of equilibrium, certain available properties like pressure, concentration, density becomes constant. This was the basic definition of equilibrium, right? Okay. Chemical equilibrium can be established from either side, from the forward side or the backward side we can establish. Okay. A catalyst can cause the state of equilibrium to be reached faster, but does not alter the state of reaction. It is just used to fasten the reaction, but it is not consumed. It is obtained as it is when the reaction completes, right? Okay. Chemical equilibrium is dynamic in nature, students. Okay. Other than this, any change in external stress, for example, pressure, temperature or concentration, causes disturbance in equilibrium state. So whenever you change them, it causes disturbance. The state of equilibrium being stable is again reached by some adjustment, which is Le-Chatelier principle. Okay, we have to attain a stable state. To attain a stable state, we will change the conditions. Okay, if temperature is changed, a new equilibrium is achieved with a new value for relative concentration of products and reactants. Okay, and if temperature is kept constant, pressure and concentration of the reactant product is altered. Okay, system shifts in forward or backward direction in order to nullify the alteration, which is our Le-Chatelier principle, that we will stop, the effect that is being occurring. Okay, we will reduce it, right? So these were the characteristics of equilibrium, students. Now comes the question time. We have covered our chapter chemical equilibrium. The very first question is, write the relationship between Kp and Kc for the following reactions. What was the formula? It was very simple. Kp is equals to Kc into RT power delta Ng. It is as it is. You just need to calculate delta Ng. It is quite simple. For the very first case, we have N2 gaseous plus 3H2 gaseous gives 2NH3 gaseous. Now what is delta Ng? It is number of moles of product minus of reactant. For product we have these two, minus for reactant what we are going to have? This 3 plus here 1 is present. So 3 plus 1, that is 4. So what we are going to get? 2 minus 4, that is minus 2. So what is the relationship for the very first one? It will be Kp is equals to Kc into RT power minus 2. Or in other terms, we can write Kp is equals to Kc by RT square. When something is in minus, you can even divide it and write in such a way to become positive. Okay. Okay. Now let us see the second part over here. For second part, 2H2O gaseous gives 2H2 gas plus O2 gas. Now what is delta Ng over here? It is, see, number of moles of product minus number of moles of reactant. For product we have 2 plus 1 as 3, minus reactant we have 2, so it comes out to be 1. So what is going to be the equation for this, students? What is going to be the equation? Kp is equals to Kc into RT power 1. So it is Kp is equals to Kc into RT. Is it clear? It was quite simple, students. It was quite easy for you to do so, such questions. Now students, we just need to establish the relationship that is simple. But in some of the questions, they give you the value for Kp and Kc, so you can equate also. Okay. Next question comes, which is 15 moles of H2 and 5.2 moles of I2 are mixed and then allowed to attain equilibrium at 500 degrees Celsius. At equilibrium, the concentration of Hi is found to be 10 moles. The equilibrium constant for the formation of Hi is. Okay, now what is happening over here? We are going to write. First of all, we know that 15 moles of H2 and 5.2 moles of I2 are mixing. H2 plus I2 get mixed up, forming Hi, right? Now H2 is 15 moles. I2 is 5.2 moles. This was initially when time was 0. Okay. Now, then allowed to attain equilibrium at 500 degrees Celsius. Now comes equilibrium. At equilibrium, the concentration of Hi was found to be 10 moles. See, initially we know that product is 0, right? So at equilibrium, that means at time t, they are saying the concentration of Hi was 10 moles. The equilibrium constant for the formation of Hi will be, so see what we do, let us say this is A, this is B. So we say that A minus X, B minus X, and we know that here 2 will come. Why 2 will come? Because we will balance this equation, and we know that whenever we are getting this number over here, here what will come? If this is X moles are dissociated, X moles are dissociated, X moles will be made and 2 is present. So 2 into X will come. Again, I am telling here A minus X and X was becoming. So here we will write, 2 will write in front of the X. And the value is given, that is 10 moles. So from here we can calculate X, which comes out to be 10 by 2, which comes out to be 5. Now we can write the value of X over here. What will come? A minus 5. B minus 5. What is A over here? A is 15 moles. Initial were 15. So between 15 minus 5 comes out to be 10. B is here 5.2. 5.2 minus 5 comes out to be 0.2. Now we have the value at time t as of H2 is 10 and for I2 it is 0.2 and for Hi it is 5. They ask you about the equilibrium constant for the formation of the Hi. Equilibrium constant was very simple. See, when volume is constant, when volume is same, so no need to take volume, right? Here, when it is nothing given to you, you have to take as a volume as 1 only. So now you have the concentration of Hi, power 2 will come because it is balanced. And here H2 will come, I2 will come, power is 1, 1. For Hi, the concentration is 5 square. For, sorry. 5 will not come. Why 5 will not come? 5 is the value of X. What is the value of Hi over here? It is 10 moles. It is 10 moles. So the concentration is 10 moles. 10 square divided by what is the concentration for H2? It is 10. It is 10 into what is the concentration of I2? It is 0.2. Again, I am telling this is the value of X that we have calculated from the concentration of Hi. The concentration of Hi was given in the question only, 10. Right, now if I solve this, it is 100 divided by 10 and 0.2 can be written as point will be go in front and 10 will go above. So it comes out to be 50. Answer comes out to be option number A, which is 50. I hope so it is clear to you. Such kinds of question comes in your examination. Now students, comes our next question. Which of the following equilibrium is not shifted by increase in the pressure? That means whenever the equilibrium is not shifted, that means delta Ng will be 0. We have to calculate delta Ng as 0 because they are saying which of the following equilibrium is not shifted. Shift will only occur when delta Ng is either more or either less than 0. But when it is 0, that means equilibrium is attained, shift will not be occur. So we will calculate the delta Ng value. For A option C, delta Ng is equals to number of moles of product minus reactant. So product here is 2 minus reactant is 1 plus 1, 2. It comes out to be 0. That means here equilibrium is seen. Here it will not shift in backward or forward. Is it clear? Great, students. Now moving to the next question. In the reaction A plus 2B gives 2C plus D. If the concentration of A is increased 4 times and B is decreased to half of its initial concentration, then the rate becomes C. It is very simple. We have this as our reaction. A plus 2B gives 2C plus D. See, we know that rate of forward reaction will be equal to what? To the rate constant into active masses of the reactant. And if they have number, it will be their power. A has 1, so power is 1. B has 2, so the power will be 2. This is our first equation. They are saying now, if the concentration of A is increased 4 times. Now comes situation part. If the concentration of A becomes 4 times, that means 4A into, and the concentration of B is decreased to half of the initial concentration. Initially it was 1, so half will be 1 by 2 of B. So now they say that then the rate becomes, what will be the value of rate? Let us see over here. K1 into 4A. 1 by 2 square is 1 by 4B. Okay, now B square will also come because B is also multiplied. 4 and 4 will be cancelled out. What will it come out to be? K1 into A into B square, which is equivalent to the first situation, initial situation. That means rate is unchanged. After changing the situation, rate comes out to be the same value. That means answer will come as option number C. It will remain unchanged. It will remain unchanged. So it is quite simple, students. The reaction remains unchanged. Is it clear to you? Because in some of the questions they are going to ask you from the law of mass action. In some of the questions they are going to correlate with you with the Le-Chatelier principle. In some of the equations they are going to ask you about Kp, Kc, about degree of dissociation, about alpha. So I want you all to make a flow chart or either make a formula sheet in which you are going to write the formulas from the very beginning to the last topic. And paste it on your cupboard, students, because it is going to help you a lot in your examinations. Is it clear? So students, this ends our lecture over here. I hope so you have enjoyed this lecture. You have already covered all of these topics now. Just the important portion is to practice. Kindly practice the DPP which I have given you. I have taken all the previous year questions in the DPP, so it will be great practice for you. Moreover, you will learn and establish that how fast you can do the questions. So sometimes what happens, students does questions and say that ma'am, my speed is slow, I am unable to do in the same pace as my friend does. So the best way to increase your speed while doing any of the questions is the practice. See, whenever you are practicing, you are revising your concepts, you are revising the formulas. So practice will establish a concentration in your mind, and with the help of that concentration your speed automatically increases. So practice a lot, students, because without practice there is nothing, and you are a competitor, you are a fighter, you can do anything in life. Okay, just believe in yourself. So we end our session with this, that practice, practice and practice. We will meet you in the next lecture, that is ionic equilibrium. Till then, keep smiling, keep learning. Thank you so much.